Hey, AP Chemsters, this is Mrs. Vanderlei bringing you another edition of the blank wall process. I am unable to be with you today, obviously, so you have Miss Vanderlei. And I guess we're going to just start off with problem number 25. Bells 1 and 2, you've already done this. Bells 4 and 5, we did not. So if you were not here on Friday, here is my rendition of number 25. If you were not here because of the leadership conference, I hope that you have talked to your friends, you have gotten their notes. Maybe today would be a good time to really zero in on things that you didn't understand and ask each other and help each other with the material. I know that the lab that we did on Thursday, the math may or may not be a little bit tricky. Help each other with that. I know that people are still asking questions on how to solve for Q, the system equals negative Q, the surroundings. Just use this time when I'm done with the notes. It shouldn't be a full 90-minute bell time to help one another and get through this. I don't know when I'll be back, so you guys got to help each other. So let's start with problem number 25. It says study the diagram below. Label each process as endothermic or exothermic. So you might be thinking, well, golly gee, why is this new material? We've been talking about endo and exo for a little while now. And what this section is talking about here is not Q anymore. It's actually called enthalpy, delta H. And when we have a constant volume situation, that Q is delta H. So this section is just reinforcing that same idea we had with Q. Now it applies to this delta H enthalpy. So again, label each process as endothermic or exothermic. Well, let's look at the first process. All right here. Let's look at this process. Whoops. What's going on? You are going from a solid, here's my solid, to a gas. How does a solid become a gas? It has to gain energy. And this might be reminiscent of these heating curves that we have done in the past. And so if here's my solid, it's going to gain a lot of energy. It's going to plateau off, and then it's become a gas. So here's my solid. Here's my gas, and you are adding energy to the system. So here's my energy, or maybe temperature, if you will, and you are adding energy. That will be endothermic. So let me write over here, this is endo. So if you're, I love my handwriting here, if you're ever adding energy to the system, yes, you would have it as an endothermic process. Well, let's look at the next part. Okay, so let's look at the next one. Now this is a two-step process. So we're going to go from, here we go, from a solid into a liquid. That's supposed to be a flat. Add more energy, and then that's supposed to be a flat. Then you're going to add more energy again. So over here, we are definitely adding more energy again, aren't we? So this would also be an endo. There we go, endo. So whenever you're adding energy in the system, endothermic. All right, so what about this one? When we go from a gas to a liquid and then liquid to a solid. Wow, that should sound very familiar, shouldn't it? Let me get this going here again. And so let's look at the first part. Here we have the gas losing energy to become a liquid, all liquid. Now it's going to lose energy to become a solid, and it's going to be all solid. This should be very, very similar or familiar, because here's my liquid, here's my solid. Where are you? There you go. Here's my solid. Even up here's my gas. Does this remind you of the lauric acid? So what's happening? That you're losing temperature. That you are, the system in this case, the water, is losing its energy to the surroundings to become the liquid, to become the solid. So this would be your exo system. And as you could probably figure out, this deposition where you go directly from a gas down to a solid would be also exothermic. Okay, so that would be your graphs that should be very, very similar. So let's go ahead and look at the next one. Oops, hang on, I'm trying to pause this. Okay, so if you look at this next system, again, very, very similar. I'd have this committed to memory. So on the left-hand side, where you notice that energy is leaving the system to the surroundings. So what do you think that Q is going to be if it's leaving negative. Work is going to be negative. Over on the right-hand side, notice that energy is flowing into the system, just as before. Q is positive, as is work. Okay, so this is a review from before, and really this problem number 27 is very similar to one that you've already done before. Let's do it real fast. Calculate the E for a system undergoing an endothermic process. So look at that. This is going to be a clue right here, in which 15.6 kilojoules of heat flows into the system, and also where 1.4 kilojoules of work is done on the system. So what are we going to do here? Delta E is equal to Q plus W, as you already know. Q is endothermic. What do you think that's going to be? Okay, hopefully you said positive 15.6 kilojoules of energy. And now what is going on next? Work is being done on the system. Well, look up here. What's happening? Work is being done into the system. Energy is flowing into the system. What did we say work is? Work is going to be going into the system. It's going to be positive also. What is it, 1.4? So if I add them together, I got 17.0 kilojoules. And please help everyone out and put a little plus sign in front of that so I know that you know it's a positive system. All right, let's go to the next page. This is where we're starting new material. Okay, so the next section is exothermic and endothermic process of molecular view. Hopefully you've already figured some of this out. If an exothermic reaction gives off heat, where does that heat come from? Well, hopefully we already talked about it's the internal energy of the chemical system, some of the kinetic and potential energy. We talked about how potential energy is a source of exothermic chemical reactions. Part of it comes from the attraction between the protons in the nucleus and the electrons of the other atoms. You can talk about the bonds. That's what we're talking about, is the bonds between the two atoms. That's where your potential energy comes from. So what happens when a chemical reaction occurs? Bonds are broken, so that you are breaking the attraction. Bonds breaking is always endothermic. So let me write this down. So when bonds are broken, let me find this. Here we go. Bonds are being broken. Oopsies. Hang on. Where's my mouse? Let's try this again. So bonds are being broken. Here we go. That is always endo. It says endo. Could you tell that? And new bonds are being made. Do you remember what we talked about with the lauric acid when the attraction is going on? That was exo. So to go from the liquid to a solid, we said that there's an attraction, and that's going to give off energy, like those magnets did, if you recall that. So you always have an endothermic process and an exothermic process. It all depends on which process is greater in numerical value, if the overall reaction will be endo or exo. So if the reaction is exothermic, then it says the organization of the protons, electrons are lower potential energy. In other words, it's more energetically favored. So if you recall, let me kind of draw over here. Where am I? Here we go. So a reaction occurs. So here, bonds are breaking, endothermic. All right, energy is being released, exothermic. So write endo here. I wish there was an abbreviation. And then exo here. Okay, so here bonds are breaking. Maybe you can write that down because I don't think I can. And over here, bonds are forming. That's your exo. So if the overall reaction is exothermic, then the idea of the new bonds, the organization of protons, electrons, those are your new bonds, are to lower potential energy. See how they're lower than how you started over here. So this whole process is an exothermic reaction. This is a state function. Do you remember what a state function was? It doesn't matter the pathway, the end result is all that makes a difference. So it doesn't make any difference how high this goes. Let me see here. Where am I? Oh, here I am. How high this goes. All right, it can go way up here as long as you end up down at the same place. Okay? We'll see these diagrams more and more later on. Don't worry. All right, let me kind of scroll up here. Now, this next section is really important, okay? And we'll probably spend some time on doing this. Stoichiometry. You love stoichiometry, right? So we know we're going to have a reaction. You're going to talk about reactants and products. So here is a reaction. This is propane, by the way. Remember, 3 carbons. This is propane, as in propane gas, okay? So it says enthalpy of a reaction. So we have, products and reactants here. Of the reaction is known as delta H of the reaction. Do you see this little RXN? That's your reaction. It's an extensive property. What does that mean? Why do I have a huge chocolate bar in my room? Because calories, because heat is extensive. It depends on how much chocolate you have. It depends on the amount of material you have. It depends on how much propane in the reaction below you have. So it says the magnitude of the delta H reaction for the whole reaction is for the stoichiometric amounts of reactants and products for the reaction written. So do you see this number right here? This tells me that if I have, ready, this is important, 1 mole of propane, this is how much energy is released. If I have 5 moles of oxygen, this is how much energy is released. If I create 3 moles of carbon dioxide, this is how much energy is released. If I have 4 moles of water being made, this is how much energy is being released. How do I know that's how much energy is being released? Well, what am I looking at? A negative sign. So that tells me this whole reaction is exo, energy is being released. So that's so important. For every 1 mole, for 5 moles, for 3 moles, for 4 moles, this is the amount of energy being released. But wait a minute. Do you always have exactly 1 mole of propane? The answer is, well, no. Okay. How much is in your propane tank? I bet it's not whatever its molar mass is, what, 36 plus 8, 44 grams. I bet you have more than 44 grams of propane in your tank, okay? So how much energy do you get? Well, more than 2,044 kilojoules of energy will be released. So how do I do this? How much energy is released if you have 20 grams of propane? All right, well, what do I need? I have grams. Did I hear you? Did I hear you? Periodic table. That's exactly right. So what do I really need to solve for? How many moles are in 20 grams of propane? I am using a tablet here, which makes my life kind of more difficult. So hopefully that you can fill in, oopsie, the numbers better than I can, but this is 44 grams in 1 mole. Okay, so actually it's like 44.11. But just go ahead and do that for me. And what do you get? Well, what's 20 divided by 44? I'm trying to use my calculator right now and I got an error. Hang on. So 20 divided by 44, and that's equal to about 0.45. Well, hang on. All right, so 0.45 looks like 3 moles. No! Oh no, what'd I just do? Hang on, I gotta quit this for a second. All right, so how much energy is released if you have 20 grams of propane? Well, I figured out over here how many moles I have. See right here, here's my moles. Hopefully you got something very similar. And so now we want to know how much energy is in 0.453 moles. Well, what has to go on the bottom? Moles. Now I got lazy, sorry guys. Moles of propane, so I'll put P down here. So this is moles of propane here. Well, look back up here. How many moles of propane do I have? I have 1. How much energy is released with 1 mole of propane? 2044 kilojoules. So go ahead and calculate. Well, I calculate. And I got, if I can find my pen again, negative 925 with 3 sig figs. Nope, 926. Make that a 6. Kilojoules of energy. So does that make sense? And hopefully your answer is yes. How do I know that makes sense? Because my 20 grams of propane is less than 1 mole, right? Wasn't 1 mole 44.11 grams like I had over here? Yes. So if I have less than 1 mole of propane, then I should have less than, up here, 2,044 kilojoules of energy being released. So that makes sense to me. So it says rewrite the equation and put energy into the equation. Well, let's go back to number 1. This is the equation that we're going to be writing with up here, number 1. So I'm going to rewrite C3H8 gas plus 5O2 gas yields 3CO2 gas plus 4H2O gas. Now, what do you notice? That this energy is released. What does it mean if it's released? It's a product. So add, don't subtract, add 2044 kilojoules. If it's a product, if it's being released, it's a product. So you're going to add it to the product side. So if it's exothermic, it's plus 2044 kilojoules. So delta H of the reaction be negative 2044 kilojoules is the same thing as putting plus 2044 kilojoules of energy on the product side. Okay? So let's go ahead and do the next problem, okay? Okay, problem number 28 says when 1 mole of methane, CH4, you ought to know what that is burned at constant pressure, 890 kilojoules of energy is released as heat. So is this endo or exo? Well, what do you see over here? It says energy is being released as heat, correct? There we go. So if it's released, it is exothermic. Very good. Hopefully you got that. So where does the energy go? From the reactants to the products. Or what you could say is maybe from the energy of the bonds to, you know, the surroundings, if you'd like to. So however you want to word that. So reactants to products. We could say maybe something like from the bonds. Where am I? From the bonds. Oops. No, stop that. There we go. To the surroundings. Okay. From the system, which is your bonds, to your surroundings. That's fine. Write a balanced equation. All right. Well, we can do that. Methane. So methane, they told us, is CH4 gas. All right. What else is needed to burn? Did you say oxygen? And what are you going to make? Hopefully you know this. CO2 plus H2O. So what else you have to include is you have to balance. Go ahead and do that. And finally, I need to put something else in. So go back, and where do I put this 890 kilojoules of energy? It's being released. What does that mean? It's also a product plus 890 kilojoules of heat. Okay? So now it says write the delta H for a process in which 5.8 grams, periodic table, sample of methane is burned at constant pressure. So what's the first thing I do? Got to do something with grams. Let's got to find out how many moles you have. And so that is 5.8 grams, periodic table. And then you have 16.05. Where did I get the 16.05 from? Yes, you're right, the periodic table. And that's 1 mole. And go ahead and figure that out. I'll divide 2 while I'm at it. 5.8 divided by 16.05. By the way, I'm going to guess it's about 0.3. Only because I'm looking at, you know, roughly 5 over 15. That's going to be roughly a third, so it's about 0.3. And I was pretty close. I got 0.36 with 2 sig figs, it looks like. So where's my pen? Here it is, 0.36 moles. Am I done? Did I answer the question? And the answer is no. What am I looking for? Calculate the delta H. What's the unit for delta H? It's in kilojoules. and that's in 0.36 moles. And this is why you had to balance the reaction, because you have to know how many moles of methane are right here. I didn't put a number there, so it's 1 mole, and it's negative 890 kilojoules. And how many sig figs are negative 890? Infinite. Okay, that's a given value. So only look at this number here to tell you how many sig figs. So 0.36 times negative 890, and I got negative 320. Where's my pen? Here it is. Negative 320 kilojoules of energy. Okay, so my units is negative 320 kilojoules, not negative 320 kilojoules per mole. It's just negative 320 kilojoules. All right, from the 5.8 sample of methane. Does that answer make sense? Hopefully, yes. Hopefully you know it's roughly a third of a mole, so my kilojoules should be roughly a third of 890, and that is correct. Okay. All right, let's see what's up. Okie dokies. Well, upon adding solid potassium hydroxide pellets to the water, the following reaction takes place. So this is written in, as a stoichiometric reaction. So notice here is where the energy is located. What side of the arrow is it on? It's on the product side. So what does it tell you right now? If it's on the product side, we can answer this real quick. It's going to be exothermic, because it's written as a product. Does the beaker get warmer or colder? Well, if it's exothermic, then it must be getting warmer. So once again, what is the enthalpy change for the dissolving, the dissolution of 14 grams of potassium hydroxide? Well, they're asking for, well, what's the delta H of the reaction if you have less than 1 mole of potassium hydroxide? So how can I maybe streamline this equation? I have 14.0 grams, periodic table, all right, and so we need to find the molar mass of potassium hydroxide. You figure it out while I figure it out. 39.1 plus 16 plus 1.01. I got 56.11. I hope you did too. In 1 mole. But am I done yet? This is 1 mole of KOH, right? So I'm not done yet. I want kilojoules. So I need to put mole of KOH on the bottom. And it just so happens for every 1 mole of KOH, you have negative 43 kilojoules of energy. See this? See, look at the units here. That's kilojoules per 1 mole. And that's what I put right here. Okay, that's 43, by the way. So I'm ready to rock and roll. I'm ready to actually calculate. So you go ahead and do that. See what you get. Did you get negative, here we go, negative 10.7 kilojoules of energy? I hope so. All right, let's go ahead and try the next one. This is a tad different. All right, I've been looking forward to a new one. And so let's do problem number 30. And how is this different? When 2 moles of ice are melted, 12.04 kilojoules of heat energy is what? Absorbed. That's right. So it's a little bit different. It is absorbed this time, isn't it? All right, so the question is, where does the energy come from to melt the ice? Well, you tell me. If ice is your system, what's giving it its energy? It is the surroundings. All right, how does it feel? Meaning, how does the surroundings feel? Cold. And there's a really good question down here at letter E that will go back to that kind of idea. So let me go put that up here. There we go. We're going to come back and investigate that. So write a chemical balance equation for this process with the corresponding delta H. All right, that's easy. So H2O solid becomes H2O liquid. But wait a minute, the energy is being absorbed. So the question is, how much energy is being absorbed? Well, let's look back up here. When 2 moles of ice are melted, 12.04 kilojoules of heat are absorbed. So I know I'm going to put energy over here. If it's endothermic, it's going to be on the, the reactant side. Now, what's going on here? Do I put 12.04 kilojoules here? No, 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 no. What's this number right here? This is not a 2, that's a 1. So if 2 moles are going to absorb 12.04 kilojoules of heat, then 1 mole of ice will absorb 6.02 kilojoules of heat. That has nothing to do, by the way, of Avogadro's number. Just a coincidence, okay? So don't get all excited. And so notice, you see why I had to divide this by 2, because when I read the problem, it says when 2 moles of ice are melted. My balance equation only has 1 mole. So why don't you try letter D all by yourself? See how you do. So why don't you pause this back, thanks, and let them work at it and see what they get. So pause this. Okay, let's see how you did. So how many kilojoules are equal to 20.0 grams of ice? Grams, periodic table, 18.02 grams is in 1 mole. And then 1 mole we said was 6.02 kilojoules. And notice it is a positive 6.02 kilojoules. It's because it's endothermic. So let's see what our answer is. 20 divided by 18.02 times 6.02. And I get 6.68 kilojoules of energy. All right, 6.68 kilojoules of energy. And that makes sense to me because this is a little over a mole. So this should be a little more than 6.02, and that's right. Now here's letter E. Now this is kind of an exciting question here, okay? Let's apply this. So explain why condensation is formed on a cold glass in the summer. Well, what's going on? The energy from the surroundings, which is the water and the air, is being used to do what? Is being used to melt the ice, or to perhaps, perhaps the water is colder than the air. So what happens? The air is going to lose energy, okay, because it's going to be from hot to cold. And if it loses energy, then what happens to the gaseous water that's in the air, the water vapor, a humid day? It's going to condense on the surface where it's going to give it its energy. So condensation is formed in a cold glass in summer because the gaseous water vapor loses energy and is placed on the water or on the glass. So I think this is maybe our last one for right now. Problem 31, an LP gas tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of the propane in the tank. So why don't you pause this? Try this from start to finish. I bet you have to write an equation, go back into a prior problem and see what that value was for propane, and then see how you do. When you're all done, Becky can start up the recording again. All right, so did you write your balanced equation? Hopefully you kind of rewrote the same one from before. Oops, I forgot the kilojoules over here. This should be kilojoules. All right, and so then I just did the math. How many kilojoules are in 13.2 kilograms? Multiplied by 1,000 grams over 1 kilogram. 1 mole over 44.11 grams of propane. I kind of left that out. Times negative 2044 kilojoules per 1 mole, and that's what I get. Again, I don't want to just kind of emphasize something. This 1 mole has to do everything. I'm sorry, wrong one. This mole. I'm watching my cat walking around here. Sorry, guys. Where is it? This mole, that mole, comes directly from this coefficient. If you balanced it and it was a 2, you'd have to put 2 in the bottom. Okay, if you balanced it and it was a 5, you'd have to put 5 in the denominator. So if whatever coefficient propane has, that's the number you put in the bottom. Okay, all right. Let's see what's happening on the next page. All right, so problem number 32. Ammonia, hopefully you know what ammonia is, NH3, reacts with oxygen to produce nitrogen monoxide and water. where the delta H of the reaction is negative 906 kilojoules. Calculate the heat associated with complete combustion of 155 grams of ammonia. Why don't you work on this, help each other out? Becky, pause the video, and when everyone seems to be done and happy, then why don't you put the video back? Okay, I thought the hardest part of this problem was actually the balancing. So NH3 plus O2 makes NO plus H2O. I had to go ahead and I balanced my nitrogens first by putting a 2 out in front, as you see here and here. And then I balanced my hydrogens by putting a 3 out here. But then to get the oxygens to work, I had 2 plus 3 oxygens. So that's 5 oxygens. So this is a 2.5. So what did I have to do is multiply everything by 2. So it's a 4, 5, 4, 6. Let's make sure that works. 4 nitrogens, 4 nitrogens. 12 hydrogens, 12 hydrogens. 10 oxygens, 4 plus 6 is 10 oxygens. All right, so after I did that, then I added my 906 kilojoules of energy, which is right here, because it's exothermic. How did I know it's exothermic? Because the negative told me so. So then it's just a matter of stoichiometry. And remember what I said in the last problem, that I inferred that, you see this 4 here? That came from the 4 moles of ammonia. Don't be lazy. Write this all down. Write down your units. So if you're dealing with ammonia, you have to use your coefficient of ammonia. So you get negative 2060 kilojoules or 3 sig figs. Okay. So let's go ahead and look at the next problem. Here we go. And it says, what mass of butane is necessary to produce 1500 kilojoules of heat? What mass of carbon dioxide is produced? Well, looky here, it's already balanced for you. Isn't that lovely? But wait a minute, what do you see here? I see a fraction. Is that normal? Well, if you want per 1 mole of butane, I would assume that's what this number right here is, per 1 mole of butane. If you wanted this to be a 2, 13, 8, and 10, you'd have to multiply this number by 2 as well, okay? So I believe the authors of this particular problem wanted to keep everything with 1 mole of butane. So let's check this out. What mass of butane is necessary? You figure it out and see how you do. When you're done, hit the start button again. All right, so in each case, you're looking for grams of butane, grams of carbon dioxide. So you know I have my given, negative 1500 kilojoules with 2 sig figs. My delta H reaction is negative 2658 kilojoules for every what? Look at this, 1 mole. Here we go again, 1 mole of butane. And then factor labeling, you need 58.14 grams, and so it's about 33 grams of butane. But look what's a little bit different. You're now talking about carbon dioxide. So you started up the same, but look at this number, whoopsie. Look at this number, no, stop. Hang on, gotta make this bigger again. Okay, so notice what happens right here. Where'd that 4 come from? The 4 comes from that 4 right there, from your balanced equation. So for every 4 moles of carbon dioxide, you release 2658 kilojoules of energy, and then multiply by 44.01 again, and you get roughly 99 kilojoules. So I'm hoping these problems are getting a little bit easier for you. Let's see what's next. Okay, folks, well, I see that this is what's next, and I think we're going to save this for the next day. So what I was going to suggest is that perhaps listening to Tyler DeWitt talking about a very similar thing, maybe 2 perspectives will be helpful. And then after Tyler DeWitt is done, he's about 10 minutes or so, Becky will give you your homework. So hopefully this is helpful. Hopefully you learned something. Hopefully you were able to follow along, and you can look forward to 6.7 on Tuesday. This is very much like what your lab on Wednesday is going to be about. Talk to you later. Bye-bye.